All right, this is going to be our second and final video on 6.4 polar coordinates. Um, we're going to finish off the bottom of the first sheet, this example 2 here. And I'm going to just have us ignore what this thing is saying here. This is from our textbook. Our textbook uses I just think it makes things more complicated than it needs to. We're going to talk about this idea of finding all polar coordinates for a point in a way that is a lot like what we've done in the past when we solved trig equations. And I think what is in that purple box right there just makes it too complicated. And I apologize if you use the key for the notes online. I kind of used that purple box, that idea what our textbook did, and I went into this deep LCD stuff and pulling GCFs out, and we're gonna do a little bit simpler here. So the first one to do, it says if the point P has polar coordinates of 3 comma pi over 3. So let's find that point P here first. I'm going to scale the circle out here. I'm going to go by halves so that that's 1, that's 2, and that's 3 right there. So pi over 3 would open up to right here. Make it look a little bit nicer. So pi over 3 would open up to right here. That's the terminal side of my angle. Since r is positive 3, since our R value is positive, we want to go 3 out on that terminal side and put our terminal point, excuse me, we want to put our point right here, 3 units away from the pole. There's our point. We're going to call that point P. So that is one way to write the coordinates of P, but there are actually an infinite number of ways to write the polar coordinates for P. One would be the point 3 comma pi over 3. That's using what they gave us, a positive r value on the terminal side of pi over 3. Let's write that using a negative r value. So if we use a negative r value of negative 3, that means that the angle that we would need would actually be this angle here. Let's see here, make sure I'm using the right one. Going on the right line here. So this would have to be this angle right here. That angle, which is pi away from our first angle, I'm going to use the standard position angle, would be 4 pi over 3. So if we open up to 4 pi over 3, that would get us to right there. But then to use a negative r value means put it on the back side of that angle, so pi away, and that would put it to that p that we already have right there. So these are both giving the same angle, excuse me, the same point right there. Both of those are giving that point p right there. Now what we're going to do is just use both of those, and this is where I differ a little bit from what our textbook did. Right or wrong for what we do, it's going to be plenty good enough. Now we're just going to say, well, I could use that 3 as my r value, that positive r value, if I use pi over 3 or any coterminal angle of pi over 3, which would just be plus 2n pi. So just adding multiples of 2 pi, that would give me all of those coterminal angles with that guy right there. And if I want to get all the coterminal angles with this guy right here, I'd have to add multiples of 2 pi to that 4 pi over 3. So the other thing I could do is use a negative r value and use not only 4 pi over 3, but all coterminal angles with 4 pi over 3. So very similar to what we did in solving trig equations, just adding multiples of 2 pi, that would give all the coterminal angles with those angles. Like I said, if you look at my notes key online, and I'll try to replace it as soon as I can. We went into some stuff using this 2n plus 1, which adds odd multiples of the period and that sort of thing. I think what we're doing, what we're going to use this for, this is plenty good enough. All right, so now to kind of the last piece of this section, which is equation conversions. Now, this is kind of actually reminiscent. I'm going to go back real quick to our 6.3 notes to what we did in this problem in 6.3. It's going to remind you a lot about this. So I know a lot of you found this kind of interesting when we squared these two equations here, and then we added them together, and magically we came up with this equation for a circle there. It's going to be kind of the same idea in this one. There's going to be a lot of smoke and mirrors here to come up with some of these ideas. And once you see it, oh man, I had no idea where we were. Let me just throw a guess out here. Nope. I think that's where we were, right there. Okay. And once you see some of these things, you're going to be able to kind of reach into your toolbox and figure out which method would be the best for the conversions that you're doing. So in this first problem here, we are given this polar equation, r equals 4 cosine of theta. If I have a second here, I'll show you what that looks like using Desmos, but let's find out what it is in a relation using x and y in rectangular form. So when it says put in rectangular form, again, that means with the x's and the y's instead of the r's and the thetas. So here's what we're going to start with. Let's start by writing, I'm going to do it right here, r equals 4 cosine of theta. All right, we're going to start just by rewriting the equation. All right, so here is trick number 1, and you're going to see why this works. And actually, normally we don't write stuff like this. This is a good section to write down what's happening in each step. We're going to multiply both sides by r. Okay, so in the next step, you'll see kind of why that's a useful thing to do. When we multiply both sides by r, the left side would become r squared, and the right side would become 4r times the cosine of theta. Okay? Kind of a strange thing to do until you realize what this thing equals right here. R times the cosine of theta is the same thing as writing x. So basically what we have here is r squared equals 4 times x. But even better, that guy we know equals x squared plus y squared. So here's what we have. X squared plus y squared equals 4 times x. Okay? Now what we're going to do is we're going to get that 4x on the same side. I'm going to come up here and get that 4x on the same side as our other variables. So we're going to have x squared plus 4x, and sorry if I blow the surprise here, but we're going to leave a space right there. And there's also that y squared. Oh, actually, that should be a minus 4x, shouldn't it? We're going to subtract it over. So minus 4x. Then we leave a space, and then we also have that plus y squared, and that equals 0 because I subtracted that 4x over. Well, you probably could tell what we're going to do right here. Because we left that big space, what we're going to do is we're going to complete the square. Okay, we're going to complete the square on just that x stuff. There's nothing to do with the y squared. We're just going to leave that for right now. In fact, that's going to stay as y squared right there. Okay, and I know I'm going to add something right there, so let's get ready to add something to the other side too. You got to balance that equation out. So remember how completing the square works. We're going to try to get a number here that would make this a perfect square trinomial. Well, that number is always half of this number squared. Okay, so we cheated a little bit, remember, and we always put that half value down here. And we took care of factoring right away. So when we go from here to here, we take half of that b value, and then when we go from there to there, we square it. So negative 2 squared is going to be plus 4. That's what I need to add to that side. Okay? And when we factor, that's going to become x minus 2 squared. So this thing factors to x minus 2 squared, which I have written right there. So in order to get that to become x minus 2 squared, in order to factor to that, I had to add 4. What I do to one side, I have to do to the other side. So we have that x minus 2 quantity squared plus y squared is going to equal 4. We're done. That's it. Let me write that thing a little bit cleaner. X minus 2 quantity squared plus y squared equals 4. That's a circle, folks. That has a vertex, a center at 2 comma 0, and it has a radius of 2. Remember, the standard form of a circle is x squared. Oh, that's if it's centered at the origin. X minus h squared plus y minus k squared equals r squared. So we can kind of see how we get our information there. The center's at 2, 0, and the radius is 2. Okay, so why did we do what we did? We multiplied both sides by r because it did two awesome things for us. It gave us r squared, which we could replace, and it gave us that r cosine of theta, which we also could replace, and then we had to do some completing of the square to figure out exactly what type of relation it was. This conic relation was a circle whose center was 2, 0, and whose radius was 2. Okay, so this whole piece of information here, I could make these notes a lot shorter if I got rid of some of this stuff. That whole piece of information goes a little bit deeper into what we just talked about. Actually, probably doesn't go any deeper. It just re-says the same things. But we're not going to look at it because that's why you're watching the video. So what I'm going to do is just in the space right here is write a couple of things that we remember from the previous page of things that are good to use, know, remember. X squared plus y squared is r squared. X is equal to r times the cosine of theta, and y is equal to r times the sine of theta. These three things are going to help us convert between our rectangular and polar equations. All right, so let's look at example 5 here. It says r equals 4 times the secant of theta. I'm just going to write that a little bit bigger. Oops. R equals 4 times the secant of theta. Okay, so in the last one, we multiply both sides by r. And actually, if we did that here, that'd give us r squared on this side, which we know is x squared plus y squared. But the issue is if we multiply this side by r, we would just have r times the secant of theta, and that really doesn't do anything for us. So here's another little trick here. This thing isn't our best friend. We don't have a nice little conversion for it up there, do we? Okay, but what we do have is a conversion for cosine. Well, guess what magically happens if you multiply this side by cosine? These guys are reciprocals. Reciprocals product is 1. So when we take secant times cosine, you're basically getting a 1. But what I do to one side, I got to do to the other side. So to get rid of secant, we're going to multiply both sides by cosine. On the left here, we're then left with r times cosine theta. Probably see where this is headed already. And on the right side, we're left with 4. R times the cosine of theta is x, and x equals 4. And remember, that's because secant of theta times the cosine of theta is actually 1, and then 1 times 4 is just 4. All right, so that is actually, we're done. That's it. That is the equation of a line. This polar equation is the equation of the vertical line x equals 4. If you don't believe me, actually, I don't have my keyboard available, so that's just going to take too long, so I'm going to get rid of this. If we have some time in class, we'll just, actually, I'm going to get Chromebooks for everybody so we can all practice typing those in, or if you got a second, go to Desmos and try typing that in. It's pretty easy. You'll see it's a vertical line. All right, 2 more here. We're going to convert this rectangular form to polar form. So what we need to do first is we're going to double distribute or multiply out both of these pieces right here, that x minus 3 squared and y minus 2 squared. I know no one here is just bringing that 2 in because that is like sacrilegious in this class. You can't just bring that 2 in. You actually have to multiply it out. Maybe at this time you're already good enough where you can multiply that out without even writing it out. If that's the case, go for it. If you remember kind of the pattern that's involved, when you square a binomial, what you're going to get is the first term squared to start with. That second term squared is going to be your last term, and in the middle you're always going to get the product of them doubled. So we know we're going to have minus 6x here. If you don't trust me, go ahead and FOIL that thing out. Let's use that same idea here. We know we're going to get y squared to start. The last term is going to be positive 4. The middle is going to be the product of those two things, negative 2y, but doubled, so it's going to be negative 4y. And those terms are all being added together right there. And this all equals 13. So now what I'm going to do is I'm going to rearrange stuff a little bit here. I'm going to put this x squared plus y squared next to each other. And I'm going to put that minus 6x. I'm just going to move that right here. Oh, actually, before we do anything, why don't we simplify a little bit here? 9 and 9 plus 4 is 13. And we have 13 on that side as well. So we basically know these 3 things are going to cancel out. And we're left with the 0 on that right side right there. So we have that x squared plus y squared. We have minus 6x. Let's get back to that purple color there. Minus 6x. Minus 4y. And that equals 0. All right, so what do we know? Well, we know that x squared plus y squared is r squared. Of we know that minus 6x, that x can be replaced with r cosine of theta, because x equals r cosine of theta. I just use that idea right there. Y equals r sine of theta. So we have minus 4 times r sine of theta right here. And all of this equals 0. Okay? I think you'd be with me so far. Here, now this last step here, this you get kind of stuck here. Well, think about what we do when we're stuck. Think back, past Algebra 2, even in this class. A lot of time factoring is useful. Even in this one, we didn't factor, we FOILed out, but it's kind of the same idea. Multiplication, division, we do some operations. So what we're going to do here is we're going to pull r out, the GCF of r out of this whole equation, which would leave us with r minus 6 cosine of theta minus 4 sine of theta, and this equals 0. And what we can do now is use our zero product property. So in other words, we can just say, well, this equals 0, or this stuff equals 0. Okay, and this is where things get a little weird. That's a 0. Because this guy, that r that we pulled out, that is part of our graph here. Remember, we're trying to come up with the polar equation here. This is a rectangular form equation, a conic relation in terms of x and y. You probably already realize that this is, we don't really need to do much here. We could say right away that this is a circle with a radius of square root of 13, and whose center is at 3, 2. So we know kind of all that stuff already. But what happens here is that r equals theta is just, when we pull that out and we're coming up with the equation of this line in polar form, that's just the pole. Okay, and I'm going to actually write that here. That's just a point at the pole, which is on our graph. I don't want to say that you can just ignore that thing, but for all intents and purposes, for what we're doing here, you don't really need to do anything with that. We're going to focus on this guy right here. Now we're going to get that thing to say r equals. Why? Because that's what our polar equations are going to be equal to, r, like our rectangular equations are equal to y. So we're going to have r equals, I'm going to add that stuff over 6 times the cosine of theta plus 4 times the sine of theta, and this is the equation. I'm going to not circle that because it makes it look like it's our final answer. This is the final form of our equation. That's going to give us a circle with those given characteristics. If you remember on the previous page, we already saw, actually 2 pages ago, no, where am I? Oh, I'm sorry, previous section, so you don't have to pull this out, just bear with me here. In the previous section, we've already seen the equation of a circle in parametric form. There it is in parametric form right there. Okay, and you can see the connection between that and our polar form here with the cosine and sine functions. In our polar form, this is the equation that we have here. All right, there. So we have a polar form equation right there. R equals 6 cosine of theta plus 4 sine of theta. That would give us that same circle. The last example that we're going to have here says, it's basically an application example of some of the stuff that we've been doing. It says, radar detects 2 airplanes at the same altitude. Their polar coordinates are 8 miles at 110 degrees and 5 miles at 15 degrees. Now, just so we understand, these are, since they are giving us polar coordinates, we've done a couple plane application problems in the last section or so that have all had bearing. These are not bearings. These are given to us as polar coordinates. So that 110 degrees is a legit 110 degrees from the x-axis. So 110 degrees goes to about right there. All right, so we know that that first plane has an angle of 110 degrees, and it is 8 miles. So this is 8 miles right here away from the pole. All right, so there's plane 1 right there. I'll draw a little plane there, whatever you want to do. There's a plane. All right, our second, there's 110 degrees right there as well. 110 degrees. Okay, our second plane has a polar coordinates of 5 miles at 15 degrees. So 15 degrees is only going to open up to about right there. And 15 degrees, but it's only 5 miles away. So that is a weird looking straight line. So that is a plane that is 5 miles away. There's my second little plane right there. Okay, and that is 5 miles away. All right, so what are we trying to do here? How far apart are the airplanes? Well, there's actually a couple of different things that we could do here. We could use some of the stuff we did with vectors in the past section and find that angle in between right there. All right, um, and then work from there. What I'd like to do, I'm just going to write down here that this is 15 degrees right there. That not 150. This is 15 degrees, and that is 5 miles away. Holy smokes. Here's that plane. And here's that 110 degrees. Okay. Can't hit fast forward enough in this video. All right. So this is what we know so far. Extend that angle down. Okay. How far apart are the airplanes? Well, what are we going to use here? We've got uh, a distance of 8, a distance of 5. We are looking for this distance right here. We have a triangle, and we can easily find this angle in between those two angles. That would just be the distance between 110, not distance, the angle between 110 degrees. And so I'm just going to call that theta down there. And theta would be whatever 110 minus 15 degrees is. Theta is going to be 95 degrees. So we have two sides and the angle between them. We have the side angle side case, so this is going to be a law of cosines problem. Okay, kind of a weird spot to put the law of cosines problem, but we just needed to learn what, if I had given this to you and we were doing law of sines, you would have no idea what polar coordinates are. So these polar coordinates give us a triangle that we're using the law of cosines to sine to find. So we've got that. Just real quick reminder of the law of cosines. Maybe pause the video, see if you can remember it real quick. C squared equals a squared plus b squared minus 2ab times the cosine of c, where c is that angle in between. So we know that we're going to have 64 plus 25 minus 2 times 5 times 8, which is going to be basically 10 times 8, which is 80. Let's just call that 80 right away. Cosine of that angle between them, which is 95 degrees. I just throw this all in your calculator. This is c squared, so you know you're going to want to take the square root of that. Okay. I'm not sure what all that stuff is. You can get that on your calc, but you should get, for c, you should get about 9.80. So we know the planes are about 9.80 miles apart. I can't remember what that rounded to. I went to the 100th. We went to 100th in a lot of our problems, so that's why I just have the 9.80 there. All right, so that is the end of section 6.4. You did a lot of stuff here. You learned what polar coordinates are. We were able to convert from rectangular to polar and vice versa. And we did that in a couple of different ways. And we also learned how to graph polar coordinates. So a lot of stuff in this section, and this is leading us into doing some pretty cool graphs in section 6.5.